The University of KwaZulu-Natal's College of Agriculture, Engineering and Science is committed to making a difference in our world, from the classroom and laboratory to the field. It provides one of the finest study and research environments on the African continent and is recognized internationally as a center of excellence. Agriculture, Engineering and Science is one of 4 colleges that make up the University of KwaZulu-Natal and is home to over 8,700 students and approximately 700 staff. 3 of the university's 5 campuses form the core of agriculture, engineering and science activities in the region. The college comprises 5 schools: agricultural, earth and environmental sciences, engineering, chemistry and physics, life sciences and mathematics, statistics and computer science. Engineering is offered on the Howard College campus, agriculture on the Pietermaritzburg, and all the other sciences on both the Pietermaritzburg and Westville campuses. Exceptions are agricultural engineering, which is offered in Pietermaritzburg, and geology, which is offered at Westville only. To compete with the best and to meet the challenges of the 21st century, South Africa needs highly skilled professionals in the areas of agriculture, engineering and science. We offer a wide array of interesting and innovative degree programs that open doors to a variety of different careers. Some degrees are unique to UKZN and are not offered at other tertiary institutions. For example, we are the only university in South Africa to offer a fully accredited agricultural engineering degree and one of only 2 universities in the country to offer a BSc in land surveying. Our postgraduate food security training program is the only one in the world, and we have the widest range of agricultural disciplines at any single South African or African campus. The choices of degree and the options on offer may seem confusing at first. Engineering degrees are more specific, and the options are usually career-focused. Emphasis is placed on training in the specific principles which engineers deal with in their professions. Engineering offers 7 different professional specializations. There are also degrees in land surveying or geomatics and property development. In science, there are structured or career-focused degrees. These include fields as varied as chemical technology, marine biology, industrial and applied biotechnology, and computer science and information technology, to mention a few. There are also more general degrees with a lot of flexibility. In this case, students have the choice of studying a BSc M stream in maths, physics, computer science, and statistics. All of these have a strong mathematical component. The other option is a BSc LES stream with a focus on the life and environmental sciences with subjects such as geography, genetics, botany, hydrology, zoology, ecology, and microbiology. In agriculture, there are various different options that involve practical and scientific applications. Students can combine science subjects with specific agricultural disciplines for a 4-year Bachelor of Science in Agriculture degree. These are more career-orientated. Agriculture and agricultural management are 3-year degrees with a higher practical component. Dietetics is a professional qualification that deals with the role nutrition plays in the promotion of health and the treatment of disease. Most degree programs across the college have field trips and projects that contribute significantly to the curriculum. This ensures that students learn in real-life situations under full field conditions. Many of our lecturers have received Excellence in Teaching awards, are recognized internationally, and are rich in practical experience. Students have access to excellent facilities that rank amongst the best in the world. 300 million rands has recently been invested in new teaching and research facilities, state-of-the-art laboratories, and improved equipment. The 30 million rands new School of Engineering building is the envy of engineering campuses across the country. Agricultural students have access to a 356-hectare research and training farm situated near the Pietermaritzburg campus. This facility provides students with hands-on training and is used extensively as an outdoor laboratory for teaching and research in areas such as animal and poultry science, horticultural science, and agricultural engineering. Adjoining Ukulinga is the Bisley Valley Nature Reserve, which supports a diversity of plant and bird species, as well as some large mammals. It provides a rich learning and research environment for staff and students. Based on the Westville campus, the college possesses unique facilities for research into higher voltage power transmission. These facilities are available in only 3 other places in the world and form part of the ESCOM-sponsored Science and Technology Innovation Park. The Science and Technology Education Center showcases the college's scientific achievements and promotes the public understanding of science, engineering, and technology within the region. The college houses a wide range of sophisticated equipment in its microscopy and microanalysis units, staffed by highly qualified and skilled technical specialists. The College of Agriculture, Engineering, and Science prides itself on its graduates who are highly sought after. In a market characterized by a shortage of qualified professionals in science and technology, our graduates are readily employed around the world in the fields of agriculture, science, commerce, industry, engineering, and research, to name just a few. Research plays a major role within the college and operates at the cutting edge of technology. The college has the highest research output in the university and produces the most research publications. There are over 60 well-established research groups and centers within the college. The African Center for Crop Improvement caters for
Okay, good evening, everyone. Welcome to the final session today on Physics Paper 1. What I'm going to share my screen with you, and I will tell you now what we're going to do. Okay, so we've already done the questions on momentum, and we've done work, energy, and power. We've also done a few examples on Doppler effect, and we did some on vertical projectile motion. So for today's session, I'm going to do a few more or 2 more questions on vertical projectile motion and 2 more questions on Doppler effect. And then I've gone through past papers and I'm looking at the MCQ, the multiple choice questions, on all the sections that will be in your June exam. Okay, so this is the one we're going to start with. So can you all see my screen? Can you see this example and can you hear me clearly? Okay, thank you. Okay, so here's the question also from It's a past paper. So I'm going to go through the examples, the 4 examples that we have, very slowly and step by step, so you can ask me questions at the end if there are any. Okay, so let's start with this hot air balloon. Okay, a hot air balloon is rising vertically at a constant velocity of 15 meters per second. When the balloon is at some unknown height above the ground, a stone is released from the balloon. The stone is observed to hit the ground with a velocity of 45 meters per second. Okay, and then they have a little diagram for us. And the first question is, define free fall. Okay, so I'm gonna just write it out again because I'm doing it. Okay, so 4.1, what is free fall? It's just motion of an object under the influence of gravity only. Okay, so as we're going through this and you doing the answers as well, you can write out your definitions or you can just say it to yourself. Okay, motion of an object under the influence of gravity, or you could say weight only. Okay, so that's what free fall is. Question 2, write down the magnitude and direction of the initial velocity of the stone when it is released. Okay, so there's 2 marks. I said write down the magnitude and direction of the initial velocity. So that stone is in this hot air balloon. So whatever the velocity of the balloon is, that will be the velocity of the stone. So the answer to the initial velocity of the stone when it's released, 4.2, is just 15 meters per second, and the direction is upwards. Okay. Okay, 4.3. Determine how high above the ground the hot air balloon was when the stone was released from it. Okay, so, okay, let me do it on here. So can I just show you the trajectory of the stone? So it's at this point, and then it goes up first, and then it falls down. Okay, now this is how we draw it. So I'm just going to label this A, B, C, and D. Okay, just for us to know the different parts of it. So B is at the maximum point, C is there where it comes back down, and D is at the ground. Okay, so once we know that, now the question is, determine how high above the ground the hot air balloon was when it was released, when the stone was released. So from A to D, and I'm going to write it here, okay? So 4.3, that's the trajectory. Should I just write that? Okay. So I'm going to take, oh, sorry. Upwards as positive. And then from A to D. Oh, sorry, A to B, because we want to find out how high. What A to D? Okay, so from A to D, I'm going to calculate the total height. And the equation we use, will you choose whichever one? We've given the final velocity. and the initial velocity. So we can calculate delta y. Okay, so I'm taking upwards to be positive, so final velocity will be minus 45 squared. Initial velocity is 15 meters per second. Upwards, plus 2, A is negative 9.8, and delta y is what I'm trying to find. Okay. Okay, so if you put that in, you will find that delta y is equal to minus 91.84 meters. And so the question is, how high above the ground? So the height above the ground when the stone was released. Is 91.84 meters. Okay, so that is determine how high above the ground the balloon was when the stone was released. And then 4.4 says determine how long the stone took to hit the ground after being released. Okay, so you could use different equations here. We'll just try to use the one that's easiest for us. And it doesn't matter if you use a different equation, okay? As long as you stick to your notation, we're using upwards as positive. So I'm going to say that VF is equal to VI plus A delta T. So VF is going to be minus 45. VI is 15. A is minus 9.8. And delta T is what I'm trying to find. Okay. And so if you do that, you'll get delta T is equal to 15 plus 45 over 9.8. And that is just 6.12 seconds. Okay, so that's how long the stone takes to reach the ground. Okay. Okay, 4.5 says, sketch the position time graph for the entire motion of the stone from the moment it was released from the hot air balloon to the moment it hits the ground. Use the ground as a zero reference point. Okay, so we want to sketch the graph from the moment that it was released until it reaches the ground. Use the ground as a zero reference point. And then it says here, indicate the following on your graph: height when the stone is released and time taken to hit the ground. Okay, so as I'm going down now, maybe you want to try drawing it out. So 4.5. So we know we're drawing the position time graph. So it should maybe be neater. Eh? Okay, so this is time. And it's in seconds. And on this axis is position. In meters. Okay, then we know that the maximum height, or the height, not the maximum height, the height that it was when it was released was 91.84. Okay, so at that point, and then we will have to put in there. Okay, sorry. $91.84. $91.84, and then I'm just going to write position like this. Okay, so that's where it was. Then when it was released, it went up for a short while, and then it fell back down. And so the shape of the graph, now you need to know this. I'm sure that you do by now. That is the shape of the graph, the position time graph. And then when it falls to the ground, so also I need to indicate the 0. Okay, that's the ground, the position on the ground, and that's 91.84 meters. And then this time here is 6.12 seconds. Okay, 6.12. So that is the complete graph. Okay, so they give you positions for the shape of the graph, for indicating what the maximum height is. Sorry, not the maximum height, the height when it was released. Okay, the height when it was released, and the time when it reached the ground. Okay. Remember to, oh yeah, we always put the arrowhead here and there, because these axes go on. Okay, so label your axes, time and what the unit is, position in meters, and the values that you know. Okay, so that was this question here on vertical projectile motion. Do you have any question? Just want to see. Okay. Okay, so that was vertical projectile. Question 3. I want to do vertical projectile question 4. Okay, so this was a question that someone asked us to do. Okay, so a ball of mass 0.06 kilograms is thrown vertically upwards from the balcony of a building, 3 meters above the ground. The ball reaches a maximum height h above the ground, as shown in the diagram below. Ignore the effects of air resistance. Okay, and so here's the drawing to show you. You can see a building, 3 meters above the ground is a balcony, and then the arrow pointing up, the stone, oh sorry, it's a ball, is thrown up, reaches a maximum height, and then falls down to the ground. Okay, question 3.1. Name the force acting on the ball while it is in free fall. Okay, and they're telling us that it's in free fall, and they're asking us, what is it? So the answer to that is the only force that's acting on it. I'm just going to write you that it's the gravitational force. You could also say that it's the weight. Okay, both answers are correct. Gravitational force. Okay, 3.2. Oh, sorry. Then it says the velocity time graph below represents the motion of the ball from the instant it is thrown upwards until it hits the ground. Okay, so now the picture above is showing you what happens, and then below it is the corresponding velocity time graph, okay, from when the ball was thrown upwards until it reaches the ground. So when you are looking at this drawing, so if we look at the graph of the velocity, okay. Oh, I have to be on here. Okay, so it starts, there's the velocity here, the initial velocity. And then the velocity is decreasing until 1.02 seconds when the velocity is 0. And then the velocity increases in the negative direction. So what we need to see in this, in the graph here, is that at time 1.02 seconds, the velocity is 0. And when we're looking at it like that, and looking at the drawing above, which shows us what happened, at 1.02 seconds, what happened? That is where the ball reached the maximum height, okay? Because after that, it started falling to the ground, and that's why the velocity is in the negative direction. Okay, so that's what we get from the graph. Okay, so write down, for 3.2, it says, write down the acceleration of the ball at time t equal to 1.0 seconds. Okay, and it's for 2 marks. So you must give the magnitude as well as the direction. Okay, the answer is, you know what the answer is. The acceleration is just acceleration due to gravity. So it's 9.8 meters per second squared downwards. Okay, so that questions asked you, I'll write down the acceleration of the ball at time t equal to 1.02 seconds, but that acceleration is the same for all time, from the moment that it was released until it hit the ground. At every moment, the acceleration was 9.8 meters per second squared. Excuse me. Okay, the next question is, consider the areas A1 and A2 shown in the graph above. Write down the numerical value represented by the difference in areas A1 and A2. Okay, so in this type of question, you need to know now, if you have the velocity time graph, then the area under that graph is going to give you the displacement. Okay, and the gradient of that graph will give you the acceleration. But when you look at this graph now and look at the picture above, what is the difference between the areas A1 and A2? So it helps that we know that the area A1 and A2 is representing the displacement. So A1 is the displacement from when the ball was thrown until it reached the maximum height, because at 1.02 seconds, that was the maximum height that was reached. So area A1 is that displacement. Then for A2, the area under there is from the maximum until it fell to the floor or to the ground. And if you look at the drawing above now, you can see that the first part, A1, represents it represents this part here. What is happening? That's the area A1. And then A2 is that part there from the top till the bottom there. Okay, and the question is, now if you look at it like that, that's what the area represents. The question is, write down the numerical value represented by the difference in the areas A1 and A2. So what's the difference in the areas? It's just this bit here. Okay, well, I should have just put the line down here. And that is just 3 meters. Okay. So to answer 3.3, write down the numerical value. The answer is just 3 meters. Okay, for 3.4, calculate the speed at which the ball is thrown upwards. Okay, so these parts are straightforward. 3.4.1, again, I'm going to take upwards to be positive, and then VF is equal to VI plus A delta T. Okay, so we know delta T, the time to reach the maximum height, and at the maximum height, VF is 0. We're trying to find VI. A is minus 9.8, and delta T is 1.02. Okay, so if you put that into your calculator, you'll get that VI is 9.996.
Dr. Pillay, can you please reshare your screen?
Oh, okay. Okay, can you see my screen now?
I still cannot see it.
Neither can I.
Oh. Okay, let me stop. Okay, can you see it now?
Yes, thank you so much.
Okay, so I'm not sure. I saw someone asked in the chat to explain 3.2.
No, I think you were doing 3.4.1 just towards the end.
Okay, okay.
Yes.
Okay, so this part 3.4.1 now is where we're trying to find the speed at which the ball is thrown upwards. And just using this equation, because we know that at the maximum point, the velocity is 0. And we know that the time taken to get to that maximum is 1.02 seconds. And then we can calculate the initial speed. And we will just call, it's 9.996. And we'll just call that 10 meters per second. Okay. Okay, so that's 3.4.1. Okay, 3.4.2 says, calculate the height h. Okay, so just to look back now at the drawing here, what we've calculated is the speed at which the ball is thrown upwards. We know what the maximum, we know that the time taken to reach the maximum. And now they're asking us to calculate h. So what we can do is we can find from the time the ball is thrown up to 1.02 second, what is the height that was reached? Okay, and then we can just add the 3 meters to get h. Okay, so that's what we're going to do. Again, I don't know if you expected to write it all the time or for that whole question, the direction upwards is positive. But I'm going to find delta y. I know the initial velocity now. And I know the time. Okay, so let's do that. So it is 10, 1.02 plus a half minus 9.8, 1.02 squared. Okay, and if you put that into your calculator, you will get 5.1 meters. So that 5.1 meters is from the time they threw the, was it a ball or a stone? The ball. It's from the time they threw the ball till it reaches its maximum height. The question was, calculate the height h. So looking at the drawing here now, h is from the maximum height to the ground. Okay, so then h is equal to 5.10 plus 3. And that is just equal to 8.10 meters. That's the answer for h. Okay, and then I just want to mention quickly, because I saw that in the chat, somebody asked me about 3.2. For 3.2, it said, write down the acceleration of the ball at time t equal to 1.02 seconds. Okay, so at time t equal to 1.02 seconds is when the ball is at its maximum height. And the acceleration at that time is just acceleration due to gravity, which is 9.8 meters per second downwards. And what I was saying was the acceleration of the ball at all, for all values of t, is 9.8 meters per second squared. Okay. Okay, now this next question we must pay attention to. It says, after hitting the ground, the ball bounces vertically upwards and reaches a new maximum height in 1.1 seconds. Okay. Calculate the work done by the ground on the ball while the ball is in contact with the ground. Okay, and it carries 6 marks. But you need to take a moment and read the question and understand what's happening and what they're asking. Okay, so you had the ball, it was thrown up, it reached some maximum height, it fell to the ground. And after it hit the ground, it bounces vertically up and reaches a new maximum height in 1.1 seconds. Calculate the work done by the ground on the ball while the ball is in contact with the ground. Okay, so what we're going to do is we're going to use the work energy theorem, right? Where we're going to say that the work that is done by the floor is going to be equal to the change in the kinetic energy. Okay, that's how we're going to solve it. But I need to explain to you now when we're talking about V initial or V final. So remember, for the first bit here, if we're looking at the motion, the ball goes up, reaches its maximum, and falls to the floor. So at that point, when the ball reaches the floor, so when it lands, what is the velocity there? So that is the final velocity after it lands, and it's the initial velocity for when it's bouncing up. Okay, let me just write this out for you, and then I'll take your questions. Okay, so this is 3.5. Okay, so I'm just going to say beforehand, when the ball is on the floor, okay, and that's what we want to know. When it's on the floor is going to do work on it. So then the work done, so the net work, but I'm going to call it work done by the floor, is equal to the change in the ball's kinetic energy. So remember, the ball comes and it lands on the floor. It has a certain velocity or a certain speed. So it has a certain kinetic energy. And then it bounces up with a different speed. So it has a different kinetic energy. And the difference between those two kinetic energies will be the work that the floor did on the ball. Okay. So let's do that. So VF is equal to VI plus A delta T. So the final velocity is 0. Initial velocity is what we're trying to find. A is minus 9.8, and the delta T is 1.1 seconds. Okay, so this is the time that it took to reach its new maximum height. So at the maximum height, VF is 0. Okay, so now we're trying to find the initial velocity at which it is bouncing up. Okay, so then VI is equal to, let's put that into your calculator and get 10.7. So initially the ball was thrown up at a speed of 10 meters per second. That's minus 9.8. And what is delta Y? If we are using 10, which was when it was first thrown up, what was the speed that it landed with? What was the speed when it was thrown up with VI equal to 10? When it was thrown up with a VI equal to 10 and then it landed on the floor, what was that velocity? And that's what we're trying to find. So, oh, sorry, I need to show you this again. So from where it was thrown up on the blue line here, back down to the green, then the displacement is just the red line here, which is just the 3 meters, but it's down, so it's -3. Okay, so I'm not sure if you've done an example like this and you're following, or you may have some doubts. Okay, but let's just do this. Okay, so this is, put that into your calculator and you get, sorry. $12.6. Oh, what's going on? 12.6 meters per second. Okay, so we've got two speeds here now. Okay, so remember that the ball was thrown up, it fell down, and then when it got to the floor, it bounced back up again. Okay. So this bouncing up here to get to this maximum, when it was bouncing up, we found what was the initial VI at which it was bouncing up. So going up here, what was the initial velocity? And that's 10.78. And then down here, 12.60 is when it was thrown, what was the V when it landed here? When it landed. So when it came down, it had a certain V, which was this 12.60. Okay, so this is 12.60 is the V at which it came down, and 10.78 when it reached the maximum height is the speed at which it bounced up. Yeah, I think that's a better way of saying it. Okay, so when it came down, it had a speed of 12.6 meters per second. And when it bounced up, it had 10.78. So what was the work done by the floor? And then the work done by the floor is equal to the change in the kinetic energy, which is equal to a half m Vf squared minus Vi squared. Okay, I hope you can do the next step before me to fill in the correct values here. Okay, for this case of the bouncing there. Okay, I hope that you are fine with those values, that it's 10.78 squared minus the 12.6. And if you do that, you'll get that the work done is minus 1.2 joules. Okay. Okay, so when the ball was thrown up and it landed with this here. That's how it landed. And then this is when it bounces. Bounces up. Okay. So when we are trying to find the change now, it would be the final, which is what it bounces up with, minus, oops, the initial, which is what it landed with. Okay, so that is for 6 marks. Sorry. Okay, are you happy with that? Do you want to ask me any questions? You're fine. I'm gonna have to just go in here so I can see. Okay, just double check your calculations. Okay, so let's go to. So what I'll do now is I'll just go on to the next set of questions that I want to do, which is the Doppler effect. Okay, so we need to do this one. Okay, Doppler 4. Okay. Okay, so we've done quite a few questions on this, but there were just 2, and somebody asked me the last time about.
Sorry.
Yes.
Someone is asking here, missing. It's saying asking about question 3.5. What was the final velocity? Not 12.60. Can you please just re-explain that quickly?
Yeah, but I did just check that calculation. The person just checked it because that is the answer. Oh, what were we doing? Vertical 4. Yeah, it's VF squared. So if the person's getting 158 and then you take the square root, you'll get 12.6. I just double checked it now. Okay, so the person who asked, if you put it in here, if you put these values into your equation, you're going to get 158. That's VF squared. So I should write here, sorry, I should say that VF is equal to 12.6. Okay.
I think that will be clear. Thank you.
Okay. Okay, sorry about that. I should have put in the extra step there. So VF squared is 158. And if you take the square root, you'll get VF, which is 12.6. Okay, but I'm glad that you are doing the calculations as we're going along. Okay, were there any other questions? Are you all fine with how we do that? Okay. Okay, so let's just do this question now on Doppler effect. Okay, so the siren of a train moving at a constant speed along a straight horizontal track emits sound with a constant frequency. A detector placed next to the track records the frequency of the sound waves. The results obtained are as shown in the graph below. Okay, so here's a graph of frequency versus time. And then we can see from 0 to T1, the frequency is 3148 Hertz. And then at T1, the frequency drops to 2073 Hertz. Okay, and then 6.1 says, state the Doppler effect in words. Oh, we're not writing it out again, but remember, it's the apparent change in frequency, in the observed frequency, because the observer and the source have different velocities relative to the medium of propagation. Okay, so you can write that definition out. And now, okay, so 6.2. Does the detector record the frequency of 3148 Hertz when the train moves towards the detector or away from the detector? So when we are looking at the graph, we can see that 3148 is the higher frequency. And then at time T1, the frequency drops to 2073. So the frequency of 3148 Hertz would be when the train is moving towards the detector. That is how we're getting the higher frequency. So the answer there is towards. Okay, and then, okay, for 6 marks, calculate the speed of the train. Take the speed of sound in air as 340 meters per second. Okay, so in this case, we're gonna have to get the values from the graph. Okay, so what we know is the train is moving at a constant speed, okay? So the source is moving and the detector is placed next to the track. So the detector is stationary. Okay, so we need to know that for our equation. Okay, so let's write out the equation, that the Doppler equation. So the frequency that the listener hears is V plus or minus speed of the listener over V plus or minus the speed of the source multiplied by the frequency of the source. Okay, so using the first value from the graph, 3148, that is equal to, and they said use the speed of sound to be 340. And what is the speed of the listener or the detector? It's just 0. Okay, so it could be plus or minus, it doesn't matter. It's 0 over V is 340. And Vs is what we're trying to find. Okay, but when it is 3148, that is when the source is moving towards the detector. So that's a minus sign. Okay, and multiplied by frequency of the source. Okay, now I will write out the same equation for the frequency of 2073. Okay, so there's one now. I would like to write it in side by side, so divide my page in half, but my writing's too big and I can't fit it, so I'm writing it underneath. Okay, so 2073 is equal to 340. I'm just going to say plus 0 divided by 340. And now, when the frequency was 2073, that was when the source was moving away from the detector. So this becomes a plus sign. and we don't know what VS is, we're trying to find it. Okay, so from the graph, we were able to get these two equations. Okay, so what I'm going to do is, you see that Fs, no, it's so big. This is the same Fs. So I'm just going to make Fs the subject of the formula. So rewrite this equation, and then I'll just equate the two because that's the frequency is the same for both. Okay, so that's what I'm trying to do. So I'm putting the colors here so we don't get confused because I can't, hey, looking at that equation now. When you write in black, Fs is equal to, so it's just going to be 340 minus Vs times 3148. Okay, so you can write it out. These two equations here make Fs the subject. So it's, let's leave a line. Oh, what is going on? 3148 multiplied by 340 minus Vs and divided by 340. That's from the first equation. And then I'll just write out the equation for the second one as well. That will be 2073 into 340 plus Vs divided by 340. I'm showing you all the steps here because this is what you will have to do. Okay. So we've got these two equations. So now we can just equate the two. So 3148 into 340 minus Vs will equal to 2073 into that, and then we can solve for Vs. Okay, so you can do that. So we'll write it here, 3148. We'll write it at the end. 3148 into 340 minus Vs is equal to 2073 into 340 plus Vs. Okay, we'll get 31. Okay, so you do all the steps to make sure that you're able to get the final answer. Okay, because the most important thing is after you've got those two, that you can find the speed to be this 70 meters per second. That's the speed at which the train is traveling. Okay, so the important part is, so you should get 69.99 or 70. What was important here was for you to be able to get these equations here. These two equations, I'll put them both in the green box. This is what is very important. You get it from the graph, and this is important. Okay, is the sign. Because if you get the sign incorrect, then the algebra won't be right. Okay, so as long as you know if it's approaching, it's going to be a negative sign in the denominator. If it's moving away, it's going to be a plus sign. And then once you've got those two, then the rest is your maths and you'll find the speed of the train. Okay. That was for 6 marks, okay? So it takes you a little bit of time. Then the last question is, the detector started recording the frequency of the moving train siren when the train was 350 meters away. Okay, so it started recording when the train was 350 meters away. Calculate the time T1 on the graph above. Okay, so we want to find the time T1, and they're telling us that it started recording 350 meters away. So the distance is 350 meters. The time that it took is T1, which they want us to calculate. And we know that the speed is 69.99. So can you do that? Yes, we can. We know that the speed is just delta x over delta t, which then just tells us that delta t is equal to the distance divided by the speed. And if you put that in, it was 350 meters, and we calculated the speed to be 69.99, and that gives us 5 seconds. Okay. So that is T1. It's 5 seconds. Okay. Okay, do you have any questions? Okay, if there are no questions, then we will stop now. We'll just take a 5-minute break. And then when we come back, we'll do a bit of Doppler effect with the red shifts and some MCQ questions just to practice. Okay, so I'll see you in 5 minutes.
Part of the UKZN experience is the opportunity to be part of a community and to network with not only our world-renowned academics, but with future game changers. And leaders. They do say that the extent of one's success can be attributed to those they rub shoulders with. Therefore, you must surround yourself with like-minded people. So, how do you become part of a community that is committed to your self-development? How do you become part of UKZN? First, you have to apply. All applications for undergraduate studies at UKZN are processed through the Central Applications Office, CAO. This is for both your course and student residence application. The application process is as follows. Step 1, consult the CAO handbook. This handbook provides a list of all qualifications available at UKZN. Step 2, have a look through the various courses offered and choose a program that interests you and for which you meet the minimum requirements. As one of the top 5 universities in the country, UKZN promotes academic excellence. So meeting the minimum requirements does not guarantee you a place to study. Step 3, find the program code linked to your chosen qualification. This is the code you need to enter in your application form. Okay, let me show you something. You see, a code has 3 parts. Example, for BCom in accounting, the code is KN-P-BCN or KN-W-BCN. Crazy code, right? Well, basically, the KN stands for UKZN, the middle part stands for the campus of your choice, P for Pietermaritzburg, W for Westport. Then BCN stands for the actual course. Make sure to get these codes right. Step 4. Use this program code when completing your CAO form, which is available from the CAO website. Your application will be sent to UKZN. You can always check the status of your application using your CAO number, ID number, or passport number on this website, www.caocheck.ukzn.ac.za. For more information, visit www.cao.ac.za. It's that easy. Pay close attention to closing dates for qualifications. For example, MVCHB closes on the 30th of June, whilst other undergraduate programs close on the 30th of September. What are you waiting for? Apply now and shape your future today.
Okay, so let's carry on. Can you see my screen and can you hear me clearly?
Yes, we can.
Thank you. Okay, so this was a question that you asked the last time. You wanted to know about Doppler effect with light. Okay, so that's what we're going to do now. Okay, I just found two questions here. Let's do this bottom one first. Let's have a look at this question. Okay, it says that the spectral lines of a star are observed to be red-shifted at an observatory on Earth. Okay, explain the term red-shifted in terms of frequency. And 2, how will the wavelength of the observed light from the star compare to its true value? Okay, so maybe, okay, let me start by doing this here. For this section now on Doppler effect with light, what is the Doppler effect for light? So if they asked you previously, they said, what was this effect, or state this effect, or state the Doppler effect in words, and then we had to say the whole apparent change in frequency. What if we were asked to state the Doppler effect for light? Then how would you do that? Or do you know what the Doppler effect is? It's very similar to what happens with sound, but with light, that's just slightly different. Okay, so Doppler effect for light. Okay, so I'm gonna just read the whole thing to you. So if you're writing it down, you can, or write in your own words, and then I'll write it out. So the Doppler effect for light is the change in frequency or wavelength, you can write either, of a light wave detected by an observer because the light source and the observer have different velocities relative to the medium of light propagation. Okay, so it's very similar to how we do the Doppler effect for sound. Okay, Doppler effect for light. Is the change in frequency and is the change in frequency, and then I'm going to put your or wavelength because you can say either and that would be correct. Okay, it's the change in frequency of a light wave. Can you please mute yourselves? When you're doing the definitions, remember that to get the full marks, you have to have all the important terms, okay? So detected by an observer. So remember when we did this previously as well, I told you that you have to mention the observer as well as the source. So Doppler effect for light is the change in frequency or wavelength of a light wave detected by an observer because the light source and the observer have different velocities. When we're talking about light now, different velocities relative to what? Relative to the medium of light propagation. Okay, so what does that mean? So light propagation just means that light is moving through there, and the medium propagation. Okay, so light's traveling through some medium to get to us. So when we're talking about the redshift, we're talking about light coming from distant galaxies. Okay, so Doppler effect for light is the change in frequency or wavelength of a light wave detected by an observer because the light source and the observer have different velocities relative to the medium of light propagation. Okay, so that's the first thing that I wanted to tell you. And then I just want to briefly, if a star is moving towards the Earth, okay, if a star is moving, okay, I should write that differently. Okay, the star is moving towards the Earth. Then what happens? If the star is moving towards the Earth, then the wavelength, oh, but now, okay, I have to write it in words. The perceived wavelength, so the wavelength that we measure. Okay, so I'm going to write the sign here because I'm not going to write the word wavelength each time. Okay, the perceived wavelength of the light wave. What happens to it? Does it increase or decrease if the star is moving towards the Earth? Okay, then it decreases. Perceived wavelength of the light wave decreases. Okay. If that happens, what happens to the frequency? You know that the frequency and the wavelength are inversely proportional to each other. So if your frequency is going to, if your wavelength decreases, it means that your frequency will increase. Okay, so I'll write the word out now, frequency. And it's the frequency of the light wave. Let me just write it. It will increase. Okay. And then what happens is, the light will be more blue. Okay, and then you call that blue shifted. Okay, so if a star is moving towards the Earth, then the wavelength that we will measure, the wavelength of that light wave decreases. Okay, and the frequency that we will measure will increase. And then the light that you see will be more blue, or it will be shifted towards the blue part of the spectrum. Okay, so you need to know that. And then the next bit is, if a star is moving, away from the Earth, then what happens? I'm not writing the whole story. I'm just going to say perceived lambda and perceived frequency. Of the light wave. Okay, so if the star is moving away from the Earth, then the wavelength that you measure, now the perceived wavelength, is going to increase. It increases. And the frequency that we will measure of that light wave decreases. Okay. And the light will become more red or red shifted. Okay. Red shifted. Okay, so once you know this, this is basically all that we need to know about these two. It's either that the stars are going to be moving towards the Earth, in which case the wavelength is going to decrease and the frequency will increase and it'll be more towards the blue spectrum. Or if the star is moving away from the Earth, then the wavelength that we measure will be increased. And the frequency we measure will decrease and the light will be more red. It will be shifted towards the red part of the spectrum. Okay, once you know that, we can answer all the questions that they ask us. Okay, so let's just do this one. Okay, the spectral lines of a star are observed to be red-shifted at an observatory on Earth. Okay, so if I can just quickly explain to you that on Earth, we have certain elements and we can measure them in the labs, and they have a spectrum. And the stars are made up of the same elements, so the spectrum is the same. And so we can compare the spectrum of whatever element it is. And just by comparing what we measure that's coming from the distant galaxy to what we have here on Earth, we can determine whether it is red shifted or blue shifted. Okay, and I just want to use this opportunity to tell you that if you find this interesting, please know that at UKZN, on the Westport campus, we have a research group who do this type of work. Okay, who get all this data from all this the Southern African Large Telescope and stuff. So if you're interested in it, we have an active group at UKZN. Okay, so back to this. The spectral lines are observed to be red-shifted at an observatory on Earth. Explain the term red-shifted in terms of frequency. Okay, so in terms of frequency, so then you would say this here now. Okay, if it is red-shifted, then the frequency we get would decrease. The frequency will be less. And if they ask you about the wavelength, you will say that the wavelength increases. So when the wavelength increases, then the distance between the wave fronts increase. So the frequency decreases. Okay, so this part here now will help you to explain this. How will the wavelength of the observed light from the star compare to its true value? Okay, how will it compare to the true value? It's red-shifted, so the wavelength will be greater. The wavelength is increasing. It's greater than its true value. Okay. Okay, so let's see if you can answer this one here now. So answer it here. It says the star is moving something the Earth. So is it towards the Earth or away from the Earth? If it is red-shifted. Okay, let me write on here. Write it in blue. Okay, so if it's red-shifted, the answer, the star is moving away from or towards, and I'm just giving you a moment for you to write this down, to fill in the answers. The Earth and the frequency of each line will it be equal to, greater than, or less than the true value and the wavelength? Okay, so when it comes to red-shifted, then it means that it is away. Okay, it is moving away from the Earth, and the frequency of each spectral line, what will the frequency be? Will the frequency be I'm just here to remind you. It's going to be less than. The frequency is going to be less than. And the wavelength that we get, what will the wavelength be? It will be greater. So the frequency is going to be less and the wavelength is going to be more. Okay, so I'm just going to put it here. Okay, so for one, I used the wrong pen. For one, the star is moving away from the Earth, and the frequency of each line will be less than. Okay, because the frequency is decreasing. So it's going to be less than its true value. And for question 2, the wavelength of the observed light will be something its true value. Will it be greater than, less than, or equal to? The wavelength will be greater than. Okay, so you can learn it just for the one and then know that the opposite is true for the other. So if it is red shifted, it means that the stars are moving away from the Earth, and the wavelength is going to be greater and the frequency is going to be less. So if it is blue shifted, it's going to be the opposite of that. More often than not, we will tell you what has been observed is that most of the light that's coming to us is red shifted. Okay, it's red shifted, which tells us that the stars are moving away from us. But actually, we're all moving away from each other. What's happening is the universe is expanding. Okay, and this is one of the reasons, one of the proofs that we have that the universe is expanding is all the red shift. Okay, so that's that question. So if you're ready, let's give this one a try. Astronomers on Earth determined that the light from a distant star has been blue shifted. Okay, blue shifted. What can you conclude about the motion of the star, as well as how the light from the star has changed due to its motion? Okay, so in this case, because there's so many options, we have to read all of it properly, right? So firstly, if it's blue shifted, what do we know? Blue shifted means that it is coming towards the Earth. Okay, we know that it's coming towards the Earth, and then the frequency is going to be higher, the wavelength is going to be smaller. Okay, so let's see the first one. The star is moving towards the Earth, yes. And the light observed to have a longer wavelength, a no. So with the wavelength, blue light has the shorter wavelength, red light has the longer wavelength. Okay, so that's not right. Towards the Earth and the light is observed to have a higher frequency, yes. Away from the Earth, no. Towards the Earth, but not enough information has been provided, so no. So it's towards the Earth and higher frequency, so the correct answer is B. Okay, so that's what I want to say about Doppler effect for light. I hope I've answered the question that you asked me. So now what I want to do in the last few minutes that we have, got half an hour, just less, is go through some multiple choice questions on all the topics that, that we've done. Okay. And I've called that ta-da. Okay. Okay, so some of them will be easier. I'm gonna write it in blue. Some of them will be easier. We'll just go through them quickly, but just for completeness, I wanted to cover all the topics. So momentum, vertical projectile motion, work energy and power, and Doppler effect. Okay, so let's go through these. Here's the first one. The diagram below shows a cricket player moving his hands downwards from position 1 to 2 to 3 while catching a ball. Which one of the following statements correctly explains why the cricket player moves his hands downwards? Okay, so he moves his hands downwards, the impulse on the ball is decreased, the change in momentum of the ball is increased, change in momentum is decreased, the time it takes to change the momentum of the ball is increased. Okay, so why he does that is by catching it at 1 and bringing your hand down to 3, you are increasing the time that it takes to stop the ball. Okay, so the time that it takes to change the momentum of the ball is increased. Okay. So that's the correct answer. Okay, the next one. Okay, so as we go through these, you're going to be answering it yourself now, right? Try to do the answer before me. An astronomer observes that the light spectrum of a star has been blue shifted. How have the observed frequency of light from the star and the distance between the star and Earth changed? Okay, so you just need to take a moment to remind yourself, blue shifted. What does blue shifted mean? And now they're talking about frequency and the distance between the Earth. So blue frequency, blue shifted means it's coming towards the Earth. It's coming towards the Earth, so the distance between the star and the Earth is going to decrease, and it's coming towards the Earth, so the frequency is going to increase. So we're looking for increased frequency, decreased distance. And so if we look here, that is B. Frequency is going to increase, distance between them is going to decrease. Okay, because we know what blue shifted means. Okay, now this is another one, just checking. Mechanics, two balls of masses m and 2m are dropped simultaneously from the same height above the ground. Ignore air resistance. When the balls strike the ground, which one of the physical quantities will be the same for both balls? Okay, they've got different masses. They have different masses, but they are dropped at the same time from the same height. So when they fall, so the masses are different. So you can see from all of these things, weight is mg, so that can't be it. Momentum is mv, that can't be it. Kinetic energy is a half mv squared, that can't be it because all of the masses are different. So it is velocity. But even if we couldn't eliminate the others, you know that when you have these two objects dropped from the same height, ignoring air resistance, they will both reach the bottom with the same velocity. Okay. I have to come out of it to go to my next page. Okay, so I'll just leave this on here because it's just one. Okay, consider the motion of a small stone thrown vertically upwards until it reaches its maximum height. Ignore the effects of friction. Which one of the following combinations of graphs correctly shows how the momentum P and the gravitational potential energy U of the stone change with time? Okay, so the stone is thrown vertically upwards. Excuse me, so as it's thrown upwards, you know that its velocity is changing, so its momentum is going to decrease. The mass doesn't change. So when you're looking at your graph, you must see, okay, the graph of P versus T has to be decreasing, and P is just mv, so it should be a straight line graph. And the potential energy, now we know the potential energy, the graph of potential energy is a curve, and they said the stone is thrown vertically upwards. So if it's thrown vertically upwards, as it gets higher and higher, the potential energy has to increase. Okay, so as we're looking at it, the potential energy is increasing. And so when we look at all these graphs, say, oh, okay, which is the one that corresponds where the potential energy is a curve and the momentum is a straight line? And then the answer will just be D. Okay, I can't write it on here for some reason, but the right graph for that is this bottom one here. Okay, where the momentum decreases linearly and the potential energy over time is increasing like that. Okay. There we go. Okay, this is the next one. Some of the questions will we go through a bit quicker because it's almost like a repetition because they're taken from different exam papers, okay, over different years. So some of the questions are similar. So here's one. A boy and a girl having different masses are initially at rest at point P. They slide down different parts of the water slide, as shown in the diagram below. Ignore the effects of friction. Okay, so there's point P to point Q. Consider the statements below regarding the boy and the girl. So 1, only conservative forces act on both the boy and the girl while they are sliding downwards. That's true. The boy and the girl each have the same gravitational potential energy at point P. No, because potential energy is mgh and they have different masses. H is the same, but M is different, so that's not true. They have different potential energies. And on reaching Q, the speed of the girl is equal to the speed of the boy. So see, that's just like the example we just did. That at the bottom, the speeds will be the same. So 1 is right and 3 is right. So if we look at our options here, 1 only, 1 and 3, 2 and 3, 1, 2 and 3. So 2 is definitely wrong. So it's B. Okay, the correct answer here. I wonder if I can write on here. Oh, I can't. Okay, the answer is B. Okay, for this question, the graph below shows how the momentum P of an object changes with time T. Okay, so we can see the graph here. And during which one of the following time intervals, measured in seconds, is the magnitude of the net force acting on the object greatest? Okay, and then it's 0 to 1, 1 to 2, 2 to 3, 3 to 4. So all the time intervals are the same. So they've given us momentum and we've got delta T and they are asking us about the net force. Okay, so before we can answer that, we need to know what the net force is equal to. And the net force is the net force is delta P over delta T, okay? The net force is delta P over delta T. So in each of these cases, the delta T is 1 second. Okay, so that's going to make it easier for us. When is the magnitude of the net force the greatest? So it's wherever the delta P is the greatest. So let's look at each one. So if you look at the region now, if we look at the region from 0 to 1 second, then you've got 20 minus 0, which is delta P is 20. Okay, over 1, each of it is over 1, right? From 1 to 2, it is 20 minus 10, which is 10. So that's the delta P. From 2 to 3, it is 0. So 3 is, oh, sorry, 3 is here. It is minus 10. The change is 0 minus 10 minus 10. And from 3 to 4, from 3 to 4, it is 20 minus 10, which is the. Okay, so just by doing in this example or in a question like this, you will work out what the delta P is. Okay. So that's how you will do that. If you get this question, just work out where is the change in the momentum, the gradient. Okay. Okay, so here's another one. A ball is dropped from a height above a floor. The ball makes an elastic collision with the floor at time t0 and bounces vertically upwards. Ignore air resistance. Which one of the following graphs shows how the total mechanical energy, EM, of the ball changes with time? Okay, so when we're reading this question, what's important here is the ball makes an elastic collision. Okay, so it's not losing any energy. So what do you know about the total mechanical energy? It's all bounces.
The kitchen door closed.
Okay, so when we have an elastic collision, then the total mechanical energy is conserved. It remains the same, which means that this is the correct graph because the value of EM is just a straight line. It doesn't change. Okay, the total mechanical energy is constant. So that is the correct graph. Okay. Okay, so let's look at this one. Okay, let's see if you can just try doing this. It says the net work done on an object to increase its speed from rest to V is W. Okay, how much net work must be done on the same object to increase its speed from V to 2V? Okay, so now you know that work is just the change in kinetic energy, right? So it's going to be, I need to write on here now. It's going to be, what? A half m v squared, and v squared is v final minus v initial. Okay, so that's the first one. It said to change the speed from rest to v, that is equal to w. That's the amount of work done. Okay, so I'll just write it here now as, so that's just a half mv squared is equal to w. Now they want to know how much net work must be done if you're changing the speed from v to 2v. So you just go put it in the equation and get it in terms of w. So I'm going to try to write all over here. It's a half m, and you're changing it from v to 2v, so it's 2v squared minus v squared. Okay, and that is a half m, and 2v squared, or 2v squared is 4v squared minus v squared, which is equal to a half m 3v squared. Okay, so that's how you get that, and you can write that as 3 into a half m v squared, and a half m v squared is just w, so that's 3w. So I'm writing out all of these steps to show you how to do these type of problems, because this is a common question they ask in the MCQ. If you double this, or you triple something, or you make it half, how does the value change? Okay. Okay, now we can go quickly through this. A small stone is dropped from rest and undergoes free fall. Which one of the following graphs shows the correct relationship between gravitational potential energy and speed and the kinetic energy and speed, respectively, for the stone? Okay, so it's dropped from rest. Okay, so we know that there are two curves. So if it's dropped from rest, as the ball is falling, the potential energy is decreasing and the kinetic energy is increasing. And then, because we know what the shape of the graph should be, that's the correct answer. Okay. You okay? Okay, last two, guys. Okay, let's see if you can get this. Is the last one on the shifting. Let's see if you can get this right, then I think you know this, red shift and blue shift. Consider the two spectrum diagrams below. So there's diagram 1. Okay, so you can see there's blue here and red on this side. And then diagram 2 is showing you the lines that are now moved from the first diagram. So diagram 1 represents the spectrum of an element in a lab on Earth. Okay, so we've got a certain element, and on Earth, if we look at the spectrum, it looks like that. It looks like the diagram 1. Okay, that's it. Diagram 2 represents the spectrum of the same element from a distant star as observed on Earth. Okay, so which one of the following can be deduced from the spectra above? The star is moving towards the Earth, it's at rest, moving away, or both are moving. So when you look at the drawing, what can you see? Okay, so we can see that blue is on the left and red is on the right. So how have the lines moved? The lines have shifted. Okay, if it didn't shift, it would have been directly under. Then it wouldn't have it. It's fine. But now what has happened is the line has shifted. And which way did it shift? So these two lines, they have moved that way. Okay. It has moved in that direction. Can you see? The line was here, but now it's gone there. So it has moved towards the red. So this is red shifted. It has moved towards the red. So what does that mean? I'm just pausing to give you a chance. It's red shifted, which means what we all know, red shifting means universe is expanding. It's moving away from the Earth. Okay. Oh, I don't know what's happening here. Okay, so that's the answer. Correct answer here is C. Okay. Last one. The diagram below shows a section of the path of a stone projected vertically upwards. Okay, so there's point 1 where it is projected, point 2 where it reaches the maximum, then point 3 and point 4 as it's coming down. At which one of the positions indicated on the diagram will the magnitude of the momentum of the stone be greatest? Okay, so what is momentum? Momentum is mv. So the mass is not going to change. So they want the momentum to be the greatest. Momentum will be the greatest when v is the greatest. So at which point here, 1, 2, 3, or 4, where is the speed the greatest? Okay, and then we all know the speed is the greatest as it is at D. Okay, and that brings us to the end of our revision lessons. I'm ready to take any questions that you may have. And I just want to wish you good luck for your paper tomorrow, okay? Okay, so I'm done from my side. Okay, so I'm gonna go onto the chats. So if you've chatted to me, you'll be able to see the screen. Okay, everyone will see it. So I'll just be able to answer some of your questions there. Okay, you're welcome here. Oh, now they can see what I actually. Okay. Okay. Are we having another lesson tomorrow? Please just check. So we've the physics part of it, because paper 1 is being written tomorrow, so there's no more physics lessons. But you must check your schedule now for when your lessons for paper 2 are. Okay, so please check the schedule, and then you'll know about that. Okay, I'm gonna stop sharing my screen. Okay, is there anything that you would like to ask me? If you want to unmute and ask, then we could also do it like that. Okay, you're welcome. Good luck, guys, for your paper tomorrow. I'd really like to get feedback from you afterwards, after you write your paper. After you write your paper, if you could send the email to the Physics Camp Helpline, just to give us some feedback of, was it helpful? What would have been better? What helped? I'd really like to know how you did in your paper. So I'd appreciate that, please. The administrator, the facilitator makes the videos available. I hope that they'll make it available early tomorrow so you can get to see it before you write your paper. Is the paper being written tomorrow? Oh, yes. I think it's the department's paper that's being written tomorrow. Okay, guys, so please can you just do the needful, which is I think to sign in the register and fill in some, what do they ask you? They ask you for some feedback, I think. So can you guys do that? And the last thing I want to say is good luck. Thank you for joining. I hope that you benefited from it. I hope that we made some things clearer for you, and all the best in your paper whenever you're writing. Okay. Okay, so bye from me.